Welcome back. In the previous video, we introduced type memory views and use them to reduce Python overhead inside loops. In this video, we'll apply that idea to NumPy arrays. NumPy is already very fast when we can use vectorized operations, but sometimes we need custom loop logic, conditions, per-value decisions, or transformations that are not easy to express as one NumPy call. If we write that loop in a pure Python, it can still be slow even if the data is stored in NumPy array. So today we'll write a small NumPy-based transformation, first in Python, then in Cython, using type memory views, and finally we'll benchmark the difference. Let's start by creating the baseline version, a normal Python function that loops over an NumPy array. This will give us something real to optimize and benchmark. Let's start with Python baseline. I'll create a file called transform-python-py. This will contain the regular Python version of our transformation function. This function takes 4 arguments. Values is the input NumPy array. Result is output array, where we will store the transformed values. And min and max value defines the range we want to clip into. Here we loop over every element in the array. Then we apply simple branching logic. If the value is too small, we replace it with the minimum. If it is too large, we replace it with the maximum. Otherwise, we keep the original value. And finally, we write the value into the output array. That gives us a useful baseline to optimize. Now let's create a small benchmark. I'll use timeit because we want a more stable measurement than a single manual timestamp. Here we create a million random floating point numbers. I explicitly convert them to float 64 because later our Cython function will expect double precision values. Then I create the output array with the same shape and type. We pass the result array into the function instead of creating it inside the function. This keeps the benchmark focused on the loop itself, not on memory allocation. For this example, we'll clip all values into the range from -1 to +1. Then timeit runs function 10 times and give us the total time. Let's run it and record the baseline. This is our Python loop baseline. Your number may be different depending on your machine, but this gives us something concrete to compare against. Now that we have Python version, let's write the same transformation in Cython using type memory views. I'll create a new file called transform-python. The logic is almost identical. Here, double values means that values is one-dimensional memory views of double values. The same is true for result. So instead of treating these arrays as generic Python objects, Cython knows that these are arrays of floating point numbers. I also type min value and max value as a double. For the loop index and the array lengths, I use PySize_t, which is the standard type for Python size indexes. And text is also a C double, so the comparison and assignment logic can happen without constantly creating Python float objects. And inside the loop, Cython can access the array data through the memory view. Now we need a small build file to compile this Cython module. Let's compile it. Now that the Cython version is compiled, let's update our benchmark and compare it against the Python loop. Before we benchmark the Cython version, let's quickly look at why this function should be faster than pure Python loop. The most important part of this function is the loop, because this is the code that runs 1 million times. There are 2 common Cython directives we can use here. The first one is bound check. Normally, Cython can check whether an index is inside the valid array range. That is safer, but it adds extra work inside the loop. In this function, our loop goes from 0 to value shape, so we know the index is valid. That means we can disable bound checking. The second directive is wraparound. In Python, negative indexes are allowed, like values -1. But in this loop, we never use negative indexes, so we can disable that behavior too. These directives can improve performance, but you should use them carefully. Only disable safety checks when you are sure your indexing logic is correct. For this example, it is safe because we control the loop bounds directly. Now let's update our benchmark and compare 3 versions. First, the pure Python loop, second, our Cython memory view version, and third, NumPy's built-in clip function. This comparison is useful because it shows where Cython fits. We don't want to pretend that Cython always replaces NumPy. Very often, the best solution is still a built-in NumPy operation. Here I'll add new import, Cython. We are importing clip Cython. We keep values the same. We need to create a few more result arrays, result for Cython, and result for NumPy. Now we add few more timed functions, one for Cython, where we're using clip Cython, and one for NumPy, where we're using default NumPy clip. Notice that I use the out parameter here, so NumPy writes in the existing array instead of allocating a new one every time. You also need to add a few more print statements to print Cython loop time and NumPy clip time. Now let's run the benchmark. The Python loop is usually the slowest version because every iteration runs through a Python. The Cython version should be much faster because the loop uses type Memoryviews and C-level variables, and NumPy's built-in clip may be even faster because it's already implemented in optimized native code. That is exactly the point. If NumPy already has a direct built-in operation for your problem, use NumPy. Cython becomes valuable when the logic is custom and cannot be expressed cleanly as one vectorized NumPy call. So let's summarize what we learned in this video. We started with normal Python loop over NumPy array. Even though the data was stored in NumPy arrays, the loop itself was still executed by Python, which made it slow. Then we wrote the same transformation in Cython using type Memoryviews. The important part was the function signature. Then we wrote the same transformation in Cython using type Memoryviews. The important part was the function signature. This told Cython that our input and output arrays are one-dimensional arrays of double precision floating point values. Because of that, Cython could access data much more efficiently inside the loop. We also typed the loop index, array length, and the temporary value, and we briefly used 2 common directives. But the benchmark also showed an important point. For simple operations like clipping values, NumPy's built-in clip may still be the best option, and that's completely fine. Cython is not meant to replace the NumPy. Cython is more useful when your logic is custom, when you have conditions, branch and pair value decisions, simulations, or transformations that are difficult to express as one clean NumPy operation. So the rule of thumb is simple. If NumPy already has a direct vectorized function for the job, use NumPy. But if you need a custom loop over numeric data, Cython with type Memoryviews can be a very powerful solution. In this video, we learned how to pass NumPy arrays into Cython, process them through the type Memoryviews, avoid Python overhead inside loops, and benchmark the result against both Python and NumPy. Thanks for watching, and I hope this series helped you understand how Cython can make Python code faster in real projects.